Before we get into part 2 of Mig Welding Basics, this is where we left off last week. Setting the machine to the manufacturer's chart recommendations for 1/8 inch steel. Got a nice sound, a nice bacon frying sound, but then setting it lower, the sound changes. Get a little bit of a rattle, more spatter. And we set it even lower, all the way down to 20, half the recommended speed, and you hear that hissing sound. That's way too little wire feed speed. Contrast that with too much wire feed speed here, where the wire is stubbing in the puddle. Hey, Jody here with weldingtipsandtricks.com. This is part 2. In part 1 of this series on MIG Welding Basics, I asked for comments so that if I glossed over things, forgot to explain things, we could address them later on. So today, I got a whole bunch of comments on that video, so today we're going to try to deal with as many as we can. One that I can't believe I glossed over is, what's a bird's nest? You know, how do you prevent it? So the bird's nest thing, it's not like what do I do in case it ever happens. It's more like what do I do when it happens. So let's talk about what it is, things you can do to prevent it. Drive roller mechanisms are similar in one aspect, and they all have drive rollers and some type of a feed tube or a guide tube that they feed wire into. Now this little area right in here, this little area from where this pinches the wire to where it enters the guide tube, that needs to be as short as possible. So this is set pretty darn close. This is a factory setting here. This is kind of how the machine came, but see, there's just not much space right there. It could be even a little bit closer. So the problem occurs when you've got too much resistance, either from a too many coils in your MIG gun, wrong size, your tip is messed up, got a ball of metal on the end of it restricting the wire feed or whatever, but it kinks right here. Once this kinks here from too much resistance somewhere in the gun or tip, then it kinks and it's just going to push wire down in here and bird's nest. So to avoid bird's nesting, there's several things that you can do. Number one, you want to have that little gap set as tight as possible between where the drive rollers pinch and push the wire and where they enter the guide tube. Also, make sure that your contact tip is not crudted up with a piece of spatter that's restricting the wire feed. Also, make sure that you have nice looping bends in your cable. And there's a liner inside this that typically in some guns it looks just like that guide tube does. It's a spiral wound steel cable. Other guns it's nylon or Teflon. Some guns it's not even replaceable. It's just a throwaway. The gun is like pitch the gun, get a whole nother gun. But that liner, if it's replaceable, replace it at intervals. When it gets the copper flash off of typical MIG wires rubs and builds up on the inside of liners, and eventually it gets gunky and really hard to push through there. We'll talk later on about maybe how to clean that out and to extend the life of a liner, or on a Sunday afternoon how to just make it work until you can get a new liner. All right, let's see if we can bang out the rest of the list here. Pros and cons of short circuit versus spray versus globular transfer. First thing we're going to talk about is short circuit MIG, because that's what most people will be doing in their shops and at home, aside from heavy industrial welding. Short circuit MIG is more versatile than any other type of MIG welding because you can weld in all positions. You can weld thick or thin metal. You can adjust the machine as you like, and you can use really small wires to get down really thin metal, even auto body type panel thicknesses. It's not the best for production or coated welds. You can fill in a gap easily going downhill. Just all depends on how you set the machine and if you use the proper size wire. Going uphill, not a problem. Vertical uphill welds are not a problem with short circuit MIG. They are with spray transfer, and we'll talk about that in just a minute. Alright, what is spray transfer? It's a different way that the metal comes off the wire. It comes off in fine little droplets, and it's really hot. It penetrates deeply, and it's mainly for heavy, thick metal and for production work. It's hot. It is a qualified process for doing coated work, whereas short circuit requires you to qualify the procedure, and it's got a deep penetration profile. What about globular transfer? Well, globular transfer is not used much in my experience. There may be some application for it, but it's mainly just a bad setting. Explain the different types of gases used for MIG welding steel and their applications. There are lots of different gases that can be used for MIG welding carbon steel, but I'm going to talk about the most common ones, and starting with straight CO2. You need a little adapter usually for your regulator with CO2 because the threads are different, along with a nylon insulator washer to keep your regulator from frosting up. It typically, at higher currents, it's not quite as smooth an arc, and it gets a little bit of spatter, and you can see right there I got a little undercut. But at lower currents with smaller diameter wires, even though there is a much tighter sweet spot that you have to adjust and tweak your settings, you can get a really, really smooth, nice arc. This particular little repair job was done with 023 wire, and then some of the arc shots are using 030 wire. But you can see how slow it is. It's a very slow build-up, but that's not necessarily a bad thing. If you're not worried about production rates and all that, all you're worried about is just making a one-off weld here and there. It gives you a little time, especially when you're out of position. It gives you a little time to make the weld and to reposition yourself. Alright, 7525 argon CO2 is probably the most common for short circuit MIG welding. That's what you'll probably get if you just ask for MIG gas at an air gas store or welding supply store. It's very versatile, meaning you can use it for really, really thin stuff like auto body panels with 023 wire, or you can get bigger wire. You can crank up to volts to 23 or so and weld some pretty darn thick stuff. The sweet spot setting on 7525 is much easier to do than on straight CO2. It's much more forgiving, a lot less spatter if you don't have it set quite right. And again, it's probably the most common, at least it is the most commonly used here in the States. Well, what about 9010? Where would you use that? Use that for spray transfer and also for pulse spray transfer. Now, spray transfer is where that wire never does meet the puddle, just coming off in hot little tiny droplets, and it's a really good process for coated work and for when you need deep penetration. You need for there not to be any doubt that you're getting penetration. And it's fast and it's hot. This is some pulse spray MIG here, and pulse kind of buffers it down where you can then weld vertical, uphill, overhead, and everything else too, but still get the benefits of spray transfer. What about metal prep? For MIG welding, it's hard to say across the board one particular level of metal preparation because it varies from situation to situation. Like there was a rust coating on this square tubing that needed to be cleaned off because I was going to do some TIG welding on it and some MIG welding. So for MIG welding, if it didn't have rust at all on it, I may not have cleaned it at all. But because I was going to do TIG welding, which requires a lot more cleaning than MIG in general, I cleaned up the weld areas to clean, shiny, bright metal with a flap disc, and that makes the TIG welding go a whole lot better than by not cleaning. However, MIG welding the same joint, you know, as long as it didn't have rust on, if it just had the mill scale, would not have been a problem. Also, anytime you're using flame cutting, you need to get rid of the dross. You do not want to MIG weld directly over that oxidized dross surface contamination from oxy-fuel cutting or plasma cutting. See, that's all nice and clean and shined up. Also, it just depends on the criticality of the application. You like that buzzword. But certain jobs are, you know, done to code or have inspection criteria and need to be cleaned up in the weld area down to clean, bright metal. Anytime you have paint, you need to get the paint off of there. You need to get it down to clean, bright metal. But it varies from one situation to another, the level of cleanliness that is required to get the job done correctly. What about duty cycle? What does that mean? Duty cycle is basically the amount of time out of a 10-minute period that a machine can weld at a certain amperage without having to let it cool off. It can be deceiving because sometimes you might look at a 200 amp machine and it might be only a 20% duty cycle at 200 amps. So it might have 200 amps. You might be able to use 200 amps for a short time period, but you're not going to be able to weld part after part after part continuously at 200 amps. So this machine is rated at 30% duty cycle at 150 amps. Now there's also a factor in there of what the ambient temperature is, and the rating, the duty cycle ratings usually use 40 degrees centigrade, 104 degrees Fahrenheit. This is a thermal arc fabricator 252i, and it's more money than the Hobart, but at 150 amps, it's 100% duty cycle, so you can weld all day long at 150 amps. So let's look at a couple of different situations here and where you might need more or less duty cycle. Here I am using that Hobart 210 MVP, and it's just a little light fabrication job with 1.5" square tubing, 1/8 wall, doing a whole lot of tacking, and then when this frame gets tacked all up, it gets welded up. But I'm only going to weld 1.5" at a time before I reposition, so the machine gets a lot of time to rest. Now here, sheet metal fabrication, a lot of tacking. Even though it's a lot of welding, it's at really low amperage, like maybe 50 or 60 amps. So having a 30% duty cycle at 150 amps, not a problem. A job like this can easily be done with a 115 volt MIG welder with a fairly low duty cycle. But contrast that to these 1-inch plates that get welded on the side of these pieces of square tubing, and you know, we used to do orders of 20 of these at a time, and once they were to this point, I would weld them non-stop pretty much, so I never hardly let the machine rest for more than a couple of minutes. And if I had a machine with a low duty cycle where I had to stop every now and then, it would have just been counterproductive. So, you know, in production work, 100% duty cycle sometimes is the best idea. What's the relationship between voltage and wire feed speed? One way of thinking about voltage and wire feed speed is hot and cold water to mix together to get a certain temperature. Okay, so there's a certain temperature that's a sweet spot that feels good to you, for instance, in your shower. So you turn up the hot water, and now you turn the cold water to achieve that certain temperature. There's always, you know, if you want more flow, you got to turn both. You can't just turn one. So that's kind of it's not the best analogy in the world, but that's kind of the way that voltage and wire feed speed work. There's a certain balance that needs to be achieved, and it changes. The settings change with different size wire and different gases and all that stuff, but there's a certain outcome you want. And so once you get that arc looking, sounding, acting the way you want it, if you need to go hotter or colder, you kind of adjust both down, both up to achieve that desired effect in the end. Hey, it's just one way of looking at it. In the previous video, I talked about what I call a crappy ground clamp. So what do I consider a good ground clamp? Well, what's a good ground clamp? Well, this is not. I mean, it works, but it's not, doesn't have much spring tension. It's steel that's just plated with copper, and when you're welding with it, oftentimes you can see a tooth spark and get hot. So I don't like the cheap jumper cable type ground clamps. This is a good deal better with this copper strap that joins the two jaws, so to keep you from losing a ground if one of them arcs and the other one's in contact. You can also pull this out this way and use it as clamping on the part, and then you've got the copper braided wire clamping on your part, and that helps for MIG welding also. The old school solid copper alloy clamps with a nice heavy spring and jaws on them are hard to beat. Any ground that you use is only as good as the area you clamp it to, so you know you got to have that area completely free of mill scale, paint, gunk. Is a 230 volt welder better? And if it is, why? A 230 volt welder is really not necessarily a better welder. It's just got more power. You can weld thicker metal. If all you're doing is, like say you got a muffler shop and all you're doing is welding exhaust pipe and mufflers, you know, actually a small welder might be fine, might be as good as or better than a big welder. One thing I do like about small MIG welders is small MIG guns. So if you were doing, like, you know, muffler work all day long, it would be important to you to have a nice small gun that was lightweight to reach up and be able to maneuver very easily in tight spots. For instance, compare these two guns. You know, this is the Tweco gun that comes with the fabricator. It's a higher amperage gun. It's really pretty big, especially compared to this gun that comes with a little Hobart 210 MVP. So You know, one of them feels a lot heavier and bulkier. One of them feels tiny and maneuverable. What about pulling versus pushing? Pushing versus pulling. Here we go. You know, that's an age-old argument. There's not a right or wrong way. They're just a little different. You know, we all know that there's sometimes you get in a position, then there is no option. You can only do one or the other. And basically, it's kind of like just know that they're a little different. You know, one's not like awesome and the other one is bad. It's just that you're going to get a little different bead profile, a little bit different penetration, and you know, sometimes a little more or less spatter. So I've done lots of testing on pushing and pulling. As long as you stay on the front of the puddle and keep that stick out short, both of them can work. So I'm not going to get into that deeply. Let's take a look at some of the testing that I did though. This was just done strictly on lap joints, using a little technique that tries to stay up in the front of the puddle with the arc. Pulling and pushing, same settings, same exact settings, no preheat on either joint. And then I cut them using a bandsaw, and then sanded them using around 120 grit flap disc, and then used a little bit of stainless steel discoloration remover, heat tint remover, to swab etch them with to reveal the weld nugget. You can also use naval jelly rust remover. It works pretty good for doing that too, and it's safer. But you can see there's just not a huge difference in the penetration or the bead profiles on any of these welds. Well, that about wraps it up for this part 2. But we're just getting started. We got a lot to cover here. You know, I'm going to get out that thermal arc fabricator pretty soon. We're going to look at some of the settings that it offers, like inductance, burn back, some things like that. We're going to weld some really thin stuff, tips for overhead, lots of stuff. So, hey, don't forget to hit that thumbs up button if you like what you see here, or hit the subscribe button if you haven't done that yet, and we'll see you next time.